All right, we're going to finish our second half of the Coulomb's law notes today. So we did the first half, I think it was actually even, yeah, it's been a little while now, a little bit last week. But we had our test and everything, so I hope that went well. If you haven't finished the test, I really want you to get it done today, on Thursday, if you can. Please let me know if you're not going to be able to get it done on time. But yeah, so today all we're doing for our notes is we're just going to do the second half of the Coulomb's law notes, which is probably one of the trickier types of problems that we will do in physics this year. Lots of steps going on, lots of X and Y components, and all of these new concepts that we're learning having to do with field. Sorry. So yeah, just follow along as best as you can. I'll do this is the entire lesson is just going to be doing this problem together, and I'll try to explain myself and go slow enough so that it makes sense. And the beauty of this is if you're ever feeling like I'm going too fast, you can just hit that pause button and get yourself all caught up, or even rewind if you need. So let's take a look at our question here. We have 4 identical charged spheres, each with a magnitude of 5 microcoulombs, and they're arranged as shown below here in a perfect square. Okay. Calculate the net electric force on charge A. So what is going to be the net electric force acting on charge A? Now, what we do in a scenario like this is we basically just fix the other 3 in place. So these 3 charges here do not move. They stay where they are. And then what is going to happen to A? Is it going to shoot off this way? Is it going to go this way? Is it going to go down this way? That's your job to figure out. Now, in real life, when we have charges like this, none of them get fixed in place, okay? But it makes our life easier for this case. We're looking at a relative type question here. We're looking at what is going to be the force on A relative to these 3 positions. It would get way too complicated if we try to keep these all freely moving. So we fix these 3 and just look at how A moves. So let's take a look here at what's going to happen to A, specifically based on these other charges. Let's take a look at B and D. These are both negative charges, and A is a positive charge. So that means that if these were stuck in place, if I forgot about these 2 right here, and I only looked at this one, then that would mean that B would be pulling A towards it like this, right? And if I excluded these 2 and only looked at this one, D would be pulling it like that. And then if I forgot about these 2 and I only looked at C, well, C is positive charge, and so is A. So C is actually going to be pushing A this way, right? Because 2 positive charges, if they're like charges, they're going to repel each other. And then obviously opposite charges attract one another. Now, there's one really important piece of information here that we don't have in this question, and it's the distance between A and C. Right here, there's a really, really important distance we need to get. Okay, I'm going to call it D, and I'm going to use lowercase d. We already have uppercase D here. So this is D just for distance. We can also, you know what? I'm going to change my mind. I'm not going to call it D. I'm going to call it R because R does come up in our formulas. I'm not only going to call it R, I'm going to call it R, A, C. R with a subscript AC. Now, all of the other distances we've been given, 25 centimeters, 25 centimeters, 25 centimeters, 25 centimeters. So let's write down some information that we know. This is how we usually start off these problems. We write down the information that we know, and then write down, what we're trying to find. So before I do that, I'm just going to decide on some directions here. We're going to just assume that this is kind of following a northeast, south, and west pattern, okay? So let's write down some information we know. We know that the magnitude of every single charge, so every single charge has a magnitude of 5 microcoulombs. What that means, I'm going to convert that to coulombs, okay? That is 5 times 10 to the negative 6 coulombs, right? Micro just means 10 to the negative 6. This is our charge. Let's write down the formula that we're going to use. This is a Coulomb's law problem, after all, right? So we're going to use Fe equals KQ1 Q2 over R squared. So that's the formula that we're using, right? So what is this telling us right here? This is technically telling us the charge of Q1 and the charge of Q2. And we don't have to worry about like a Q3 and a Q4 or a QA, QB, QD, QC. We can, but every single time we do one of these problems, we're only ever going to be treating two of them at once. We're only ever going to be looking at the force of A due to B. We're ever looking at the force of A due to B. Okay? And what that would mean then is that maybe Q1 is A and Q2 is B, right? So this could maybe be QA and QB. But no matter what, it doesn't matter. I could even write this here. It could be QA, it could be QB. It told us in the question that they were all the same, right? So it doesn't matter. All of them are the same. It's all of those. 5 times 10 to the negative 6. That's the important part, okay? So let's write down, let's just remind ourselves what's K equal to. K is 9. Now we're going to use the value for K that has coulombs in it, right? We're not going to use the electric charge one. So, or elementary charge. I mean, I hear it used both, so you can use either. 9 times 10 to the 9 Newton meters squared per coulomb squared. That's our coulomb's constant. Okay, 9 times 10 to the 9. And then what is our distance? So we have RAB, we'll call it RAB. Probably use, I don't know why I've been using lowercase a. That should be uppercase a. This is going to happen throughout this problem. I'm going to notice just some little things that I should be doing differently. It's been a while since I've had a problem like this. So RAB, we've got RAD, that's the distance between A and D, and then we've got RAC. I want all of my R's, all of my distances to be in meters. So if I have 25 centimeters, that means that my distance is just going to be 0.25 meters. So that's the distance from A to B. Also the distance from A to D, 0.25 meters. What's my distance from A to C though? And what you actually need to do here to be able to figure it out is look at this little triangle here. You've got 25 centimeters, 25 centimeters. You just need to find the hypotenuse, right? And in fact, looking at that, we actually know that this angle right here is going to be 45 degrees. Because if it's a perfect square, that means that this is going to be 90. Cutting that in half is going to give us 45. That'll be important later. So RAC then is, we're using Pythagorean theorem. It's the square root of 0.25 squared plus 0.25 squared, right? So that's our distance from A to C. And if we do that, if we plug that into our calculator, don't round off your answer too much. Leave several decimal places because you're going to be using this number a lot. 0.3536 meters. So there we go. That is all the information that we need to be able to do this problem now. Now is kind of the tough part. Now we need to actually start. So let's take a look at, I guess, one last thing that we should write out. Our final answer that we're trying to find is the net electric force on charge A. So we're trying to find a combination, right? We're trying to find F net A. And it's going to be a vector. That means that we need to find FAB. We need to find the force of B on A. We need to find the force of C on A and the force of D on A. So we need to find FAB, FAD, and FAC. Hopefully I've left myself enough room here. Okay, let's get started. Let's start with the two easier ones. I'm going to call these ones easier because they're going to be the exact same. The only difference is that B is pulling it to the east and D is pulling it south. So let's start off with FAB. What is FAB? Well, FAB is K QA QB over RAB squared. So what that is is, I wonder if I can, I'm probably not going to have enough room. I'm going to have to write it below here. So K, which is 9 times 10 to the 9, times QA, which is 5 times 10 to the 6, to the negative 6. My apologies, the negative 6. And then QB, which is also 5 times 10 to the negative 6, over the distance between them, which is 0.25 squared. And if I do that, I should get that the force of B on A is 3.6 newtons, and it's pulling it, we already decided this, it's pulling it to the east. So 3.6 newtons east. So there is one very important value. Now, the beauty of this is FAB, is that it is the exact same as FAD. The only difference is that it's 3.6 newtons and it's being pulled by D, it's being pulled south. So there's another important piece of information that we get basically at the exact same time. So we've got two of them. We just need to find FAC. FAC is the toughest one, but only because it's a different distance and it's also going to have an angle associated with it. So let's find FAC. It's really actually not that much. FAC is going to be, I'm going to write it all out again. K, Q, A, Q, C over R, A, C squared. So that's 9 times 10 to the 9 times QA, which is 5 times 10 to the negative 6, times QC, which is 5 times 10 to the negative 6, over RAC, which we found right here, is 0.3536 squared. And if I do that, I plug it all into my calculator. I've already done this beforehand. I should get something that looks like 1.8 newtons. And then my direction going back up here, remember, it's pushing it away, pushing it up here. So based on this 45 degrees, well, this is also going to be 45 degrees right here. So pushing it up, it's going to be west 45 degrees north. So that is FAC. Let's put a square around that. And let's just remind ourselves that's FAC. Okay, now there's something very, very important that we need to do next. Now we're trying to find F net of A. If I'm ever trying to find the F net of something that's acting in multiple directions, what do I always do? I need to always split it up into its X and Y components. Always split it up into its X and Y components. So we're going to try to find F net X, and we're going to try to find F net Y. So F net X and F net Y. I'm going to leave these as scalars because I'm going to use positive and negative values in there. Now, before I can do that, I need to separate this. I need to turn this into its X and Y components, right? So I'm going to redraw what I have up here. So I've got this little A charge, positive A charge, and it's being pushed up that way, 1.8. And if this right here is 45, that also means that this right here is 45. So we'll just go down here because I accidentally wrote my 1.8 up there. Doesn't make a difference. We're going to have an X component and we're going to have a Y component. And we've done this a bunch. So I do think that we should at this point be able to know what's going to happen here. This is the adjacent, this is the opposite. So this is going to be 1.8 cos of 45 degrees, and this is 1.8 sine of 45 degrees. Okay, I'm going to put a little box around this so we don't get that confused with everything else. Now, remember that this is going east and this one's going to be going west, and this one's going south and this one's going to be going north. So they're going to subtract from one another. So let's just go up here and let's decide on a positive and a negative direction. Let's say that west is negative and south is negative. That's kind of what we normally do. And these are my positives. Okay, so let's add them all up now. Let's add them all up. So F net X is going to be 3.6 newtons east, which is positive 3.6, plus negative 1.8 cos 45. Okay, negative because it's going west. So I could have just put the negative there, but I'm just going to do it this way. So negative 1.8 cos of 45 degrees. And then for my y, I've got 3.6 acting downwards. So negative 3.6 plus, and then this is also going to be positive because it's north. So positive 1.8 sine of 45 degrees. So if I do both of those, what you're going to end up noticing actually is that you end up getting, for the top one, you'll get positive 2.327 newtons. And for the negative, or sorry, for the y, you'll get negative 2.327 newtons. So all that's actually telling us is this positive and the negative are just telling us directions. And we've already decided on directions, east and south. So what this is basically telling us is that this charge is going to feel a 2.327 Newton force to the east and a 2.327 Newton force south. So our net force on A is going to look something like that. F net A, and with an angle there. Okay, so our last step, our absolute final step here, is just going to be to find F net A by doing Pythagorean theorem. So we'll do the square root of 2.327 squared plus negative 2.327 squared, but that's just going to get squared, so it doesn't matter. And that's going to give us 3.3 newtons. We'll do theta as well. Theta is going to be the inverse tangent, so tan to the -1 of the opposite over the adjacent. Basically, what that's just going to give us is 2.327 divided by negative 2.327. Which is just tan inverse of -1. If you do that, you'll get negative 45 degrees. That just means that it's 45 degrees, in our negative, quote unquote, negative direction. So 45 degrees. Okay, so then our final answer, F net A. I guess I shouldn't have put my vector arrow up there. We're going to do the vector arrow here because now we're going to have the direction. And after all that work is 3.3 newtons east, 45 degrees south. So that is quite the question. It's got lots of steps to it, and you actually end up getting a pretty kind of predictable answer in a way, in the sense that, looking at it from the start, you realize that the A's and the B's, the B and the D charge are, they're all the same magnitude and size, and they have the same distance, right? So the way that they affect it with just another charge, obviously they're going to be affecting it the same way, just in the X and Y directions. So there's your final answer. That's a tough one. And in your practice problems, I believe in practice problem 7 and 8 are very similar to that. And arguably 8, actually not even arguably, 8 is more challenging. So 8, you'll even see on there, it says you can try it, but it's pretty difficult. I'd like you to give it a shot, but don't get too discouraged if you don't get it. The difficulty of questions you'll be seeing on the assessments will be kind of, what you've been seeing all year. It'll be more like this difficulty. So that's always the case, though, with the practice problems. As we get further into them, they do become more challenging, and that's just for me trying to, give you a little bit more of a challenge if you need it. So I hope that helped. Have a great rest of your day. I'll talk to you tomorrow.